In this tutorial, we will learn how to evaluate whether there's evidence of incremental validity using a multiple linear regression model. And so to get started, we're going to be working with this toy data file here, which is called concurrent validation with a capital C and a capital V, and this is a comma-separated values or .csv file. Note that concurrent validation here indicates that these data that you see here pictured in this data file were collected as part of a concurrent validation design, which means that the predictor variables, which in this case are employee selection tools, and the criterion variable of job performance were all collected at about the same time with current employees in this case. So if you haven't already, save the data file that you're going to be working with into a folder that you can subsequently set as your working directory. I've already saved mine into a folder that I call my R workshop folder, and it is within my H drive. And so you can see right here, here's the path, my H drive, R workshop folder, and here's the file. As you can see, it's a comma-separated values file, as I mentioned earlier. All right, so let's get into RStudio now. All right, so you open up RStudio here, you should see that we have our console open. Let's go ahead and clear out the default text that's in our console about the version history and so forth by going to Edit and Clear Console in the drop-down menus. The next thing we're going to do is we're going to go to File, New File, and R Script. Again, the drop-down menu directions are File, New File, and R Script to open up an R Script editor window. This will allow us to make annotations, track our work, make our work more reproducible, and easier to share with colleagues. I'm also going to go here to the View drop-down menu. I'm going to zoom in a bit here, so hopefully it's a little bit easier for you to see what I am typing. All right, so the first thing I'm going to do is note what is the purpose of this tutorial, which I mentioned at the top of the video, which is we're going to be evaluating incremental validity and specifically evaluating whether there's evidence of incremental validity using a multiple linear regression model. So let's first do a quick conceptual overview of what a multiple linear regression model is and when we use it and why we use it. So like a simple linear regression model, where a simple linear regression model has just one predictor variable and one outcome variable, a multiple linear regression model can also provide us with information about the strength and the sign of linear associations between predictor and outcome variables. However, instead of having just one predictor variable and one outcome variable, as is the case with a simple linear regression model, in a multiple linear regression model, we have two or more predictor variables and still just one outcome variable. Now, these models are going to allow us, and specifically I mean these multiple linear regression models are going to allow us to infer the association between each predictor variable and the outcome variable while statistically controlling for the associations between other predictor variables and the same outcome variable that are specified in that same model. And this is where the concept of incremental validity comes into play. So in this context, incremental validity refers to instances in which a predictor variable explains a significant amount of variance in the outcome variable, even when statistically controlling for other predictor variables in the model. In other words, if we find that a predictor variable still significantly predicts or is associated with the outcome variable, even in the presence of other predictor variables in the model, this gives us an indication that this predictor variable can explain variance in the outcome above and beyond what the other predictor variables are able to do. Now, incremental validity can also refer to situations in which we actually have a block of multiple predictor variables explain incremental validity above and beyond a previous predictor variable or multiple predictor variables. And this is typically called hierarchical linear regression when we run models like that. And it's actually separate models that are nested when we're testing those types of, when we're testing incremental validity in that context. But here we're just going to focus on a very simple instance of incremental validity, which is when we have a single multiple linear regression model, which means we have two or more predictor variables. And so by default, we can test incremental validity and whether there's evidence for it using such models. So what's the relevance for employee selection in a human resource management context? Well, evidence of incremental validity signifies that a selection tool explains unique variance in a criterion or outcome variable when accounting for the effects of other selection tools that have been specified as predictors in that model. And this is another way of checking to make sure that any one selection tool is not redundant with other selection tools the organization may want to use. And so if you think of a resource perspective and efficiency perspective, this will make things hopefully more efficient for an organization and exhaust fewer resources when we can make sure that each selection tool we're using to try to predict future employee job performance, for example, make sure each one of those selection tools is going to do something unique and help make unique predictions in that regard, and not make predictions that would be redundant with what one or more of the other selection tools might make. So behind the scenes here today, when we run our multiple linear regression models, we will estimate what's called an ordinary least squares, or OLS, multiple linear regression model. And OLS simply refers to the process of estimating the unknown components, or in other words, parameters of the regression model by attempting to minimize the sum of squared residuals. So really what we're trying to do here is to fit a model that minimizes the errors or the residuals between the predicted and the actual outcome values. Because at the end of the day, because we have just that one outcome variable and we have multiple predictor variables, we really are trying to, we do have the ability to make an equation based on our regression estimates or parameters that we estimate. And we can then make that equation or formula, plug in new values, and make predictions for that outcome variable when we start receiving new data for each one of those predictor variables that we have in the model. Okay? And so, but what we're trying to do with just a single model with one data set, we're really just trying to take what are the predictions we would make by the model. In other words, what is the linear prediction? So you can think of that line of best fit if you're thinking of a scatter plot and a superimposed line to best fit the data that will minimize the error so that we have fewer errors or less overall error on average between our predicted and our actual outcome values. So I do want to mention at this point the statistical assumptions that do need to be met when we are running or estimating and interpreting the findings from a multiple linear regression model. We're not going to cover these in detail or test them formally in this tutorial to keep things, keep the time lower, and also because this can be a quite exhaustive process. However, this is an important thing that you would typically want to do, and fortunately, the regression function that we're going to be using today from the lessR package does a nice job of providing a number of plots and diagnostic statistics and information by default whenever we run it. And so you can use that information to test some of these assumptions that you see here. So the first assumption is that the cases or the observations are randomly sampled from the population. And this really has to do more with your sampling strategy. For example, if you use a random sampling or probability sampling approach, you're going to then hopefully be able to assume that there's an equal chance or approximately equal chance for each observation to have been included in the sample from the underlying population. We also want to make sure that we meet or satisfy the second statistical assumption, which is that there are no multivariate outliers. We also want to make sure that we satisfy the third assumption, which is that there is a linear association between each predictor variable and the sole outcome variable. Also, we don't want there to be any collinearity, which is sometimes called multi-collinearity, between the predictor variables themselves. And when I say no collinearity, it's fine to have some collinearity or correlation between the variables. In fact, we will look at that here today. But when you have concerning levels of this, you run into an issue where essentially the predictors could be somewhat redundant with each other, and they're fighting over variance and variability between themselves. The fifth statistical assumption that should be met is that the average residual values, so these are those error values when we're trying to compare the actual observed values on our outcome variable with what we would predict based on the model that we're estimating. We want the average residual value to be 0 for each level of the predictor variables. The next statistical assumption is that we should satisfy that the variances of the residuals are equal for all levels of the predictor variables. And then finally, we want to make sure that the residuals are distributed normally for each level of the predictors. Okay, so with that said, we're ready to get into first setting our working directory, then reading our data into R in the R environment so that subsequently we can reference the data frame that we read those data in as so that we can run and estimate a multiple linear regression model. Okay, so the first step here is going to be to set our working directory. And I will use the setWD function from base R which means we don't need a special package to access this function. It's just set WD all lowercase, and within the function parentheses, type quotation marks. And then if you know your path for the folder where you've saved the data file that we're going to be working with today, go ahead and put that path into the quotation marks here. In my case, it's my H drive, our workshop folder, which I showed you earlier in this tutorial. And so if I run this as is, no error message down here. I've successfully set my working directory to that folder in my H drive, which is called our workshop, where I saved the data file that I'm going to be working with today, which was called concurrent validation. Now, alternatively, if you go to Session, Set Working Directory, and Choose Directory in the drop-down menus, again, that's Session, Set Working Directory, and Choose Directory in the drop-down menus, you can open up this window here, and then you can look through your files and try to find, or your folders, and find the folder where you save the data file. Once you find that folder, just go ahead and click Open. Here I am. You can see it's my H drive. Our workshop folder is where I've landed here. Click Open, and that's another way of doing the same thing. Next, we're going to read in the data file. Okay, so we're going to read in that concurrent validation, comma-separated values file that I showed you at the beginning of the video. And so the first thing that I'm going to do here is type in a name of an object that I can assign the data frame to once it's read in. So I'll just keep this simple and call the object df, and just lowercase d, lowercase f, and I'll use the left-handed arrow operator so that we can assign what comes to the right of the arrow to this object that I've called df here. So I will use the read.csv function from lessR. So it's read.csv, all lowercase, and within the function parentheses, type quotation marks, and within those quotation marks, make sure that you get the exact name of the data file, which the data file I'm working with here is called concurrent validation with a capital C and a capital V, which you can see pictured here in the folder that I just set as my working directory in this session. So I'm actually just going to copy the exact name of that file and paste it into the quotation marks here to make sure I get it exactly right. And I just need to remember that I add on the .csv extension because it is a comma-separated values file. Once I have that in place, go ahead and click Run. If everything goes well, you should see blue text in the console, which we do see here. And come over here and we can see we now have an object in our environment, and it has 300 observations or cases and 5 variables. In this case, each observation corresponds to an individual person or employee in this case. And if we click on this arrow here, we can get a little preview of the variable names and so forth and their variable types. So we see employee ID is a type character, and the rest are type integers, which is a specific type of numeric variable. All right, so let's click on the name of this object here so we can view it in our Viewer tab here. And you will see that we have a unique employee identifier variable that is called employee ID here. And this is just meant to signify that each row here represents an unique employee. The next variable over is SJT, which stands for a type of selection tool, employee selection tool, which is called a situational judgment test. And let's assume for this case that this situational judgment test is meant to tap into or assess the construct of emotional intelligence in people who take this test or participate in this test, as well as their empathy. And the potential scores can range from 1 to 10 here. Okay, so from 1 to 10, where 10 means higher levels of emotional intelligence and empathy. The next tool, or the next variable over, is a selection tool called EI, and this stands for emotional intelligence. And notice that both of these variables so far, SJT and EI, have all caps here for their names. So EI, emotional intelligence test, this is more intuitive. This is meant to assess each person's emotional intelligence. Well, that should be a little bit of a giveaway here that we might have some problems in terms of collinearity or higher than acceptable level of correlation between these two variables, because I noted that the SJT, or the situational judgment test, is also designed to assess emotional intelligence as well as empathy. The third variable here is our third selection tool, and it is called interview here. And it is meant to, let's assume that it's meant to assess interviewees' level of interpersonal skills, and it can range from 1 to 15, where 15 means higher levels of interpersonal skills. Oh, and I should say that the emotional intelligence variable can range from 1 to 10, 10 being higher emotional intelligence. And then finally, we get to our criterion variable, which is our outcome variable. In this case, it is employee job performance here. And let's assume that it represents current job incumbents, or the employees, in other words. This is their performance evaluation ratings by their supervisor. And this can range from, let's say, at the low end, possibly 1, which would mean does not meet performance standards, all the way up to, let's say, 30 at the high end, which would mean that it does meet performance standards. As you can see here, no one actually scored a 30 or a 1 in this sample of employees. And so again, we have 300 employees here, or observations, in our sample. So hopefully that gives you an idea of the kind of data that we're working with here. Now we're ready to start specifying our regression model. And because we're going to be using the regression function from the lessR package, we need to install that package if we haven't already. And to do so, we use the install.packages function from baseR. And within the function parentheses, type quotation marks and the exact name of the package we wish to install. The exact name of the package is lessR with a capital R. I have very recently installed this package and updated it, so I am not going to install it again here to save time. But if you have not recently installed this package, or you need to update it, you believe, go ahead and run this. It'll take probably 30 seconds at most on your machine, and you'll be good to go. The next thing I'm going to do, and you'll definitely need to do this part, is type in the name of the library function from baseR, and then within the function parentheses, you can just type the exact name of the package that you have installed, which is lessR with a capital R. You don't need to put quotation marks around the package name here, and then you can click Run. If all goes well, this package is a little bit unusual when you load the lessR package, because you'll see red font or text down here in your console, and this is just basic background information about Professor David Gerbing from Portland State University, who developed this package, and as well as the website that he hosts where you can access more information about this package, learn more about the book that's associated with this package, and so forth and so on. All right, so now that we have installed the package, and I'll make a note here that this line of code down here is to access the package when we use the library function. So just added another annotation there using the hashtag symbol there. And now we are ready to estimate the multiple linear regression model. And as I mentioned before, we're going to be using the regression function from the lessR package, and it's regression with a capital R is the name of the function. So again, regression with a capital R. Hopefully that's easy to remember. And then the first argument within this function is we specify our multiple linear regression model. And there's a specific way that we do this. First, we type in the exact name of our criterion or outcome variable, which in this case is performance with a capital P. Then we type in the tilde symbol, which is the squiggle symbol that you see there. And typically it's towards the left-hand corner of your keyboard on most keyboards. And I'll actually zoom in for a second so hopefully you can see this a little bit better, because sometimes it looks more like a dash, but hopefully you can see what that notation looks like there. And now I'll zoom back out. Okay, so we always put our outcome variable to the left of the tilde symbol, and our predictor variables come to the right of the tilde symbol. And our predictor variables in this case are going to be our situational judgment test variable, our emotional intelligence variable, and our interview variable, as these are our three selection tools. And let's assume our goal here is to see do each one of these tools show evidence of incremental validity in terms of explaining variance in this outcome variable of performance when controlling for the other predictor variables in the model? And then B, what is the collective level of variance that they explain in this outcome variable called performance here? Okay, so the names are, again, they are capital SJT, and actually I'll type in down here in the console just to make sure I get the names exactly right. I'll use the names function from baseR, just names all lowercase, and the exact name of the data frame that we're working with that we named here, which is called DF. Hit enter or return, and this just gives me the variable names, and I can just paste these in here. And for each additional predictor variable, you use the plus symbol or the plus operator, and you add additional variables. And so SJT, EI, and then the third one is interview. And then finally, we had another comma, so we can get to our second argument here. Our second argument is going to be data equals, and the name of the data frame to which all of these variables in our model belong, which in this case is called, we named it df. So put that in next to data equals. And the next thing I'm going to do is I am going to run that script there. And what you'll see is by default, as I mentioned earlier, you're going to get a lot of helpful plots. We're not going to work through each one of these. These can be diagnostic plots that help you assess linearity as well as collinearity and whether there's evidence of normality in the residuals and so forth. And if you scroll over, you can see these plots here. So these are your fitted values on the x-axis with your residuals or your errors on the y-axis here. And here's one where you can assess the normality of those residuals and so forth and so on. So again, we're not going to get into those today for efficiency's sake, but typically if you're working with real high stakes data, it's important to make sure that you are at least somewhat confident that you've met or satisfied the statistical assumptions for multiple linear regression that I mentioned above there. All right, so what we are going to do is start unpacking all of the output. And when I say all, there is a lot of output that comes with this function, which is one of the reasons why I'm showing you how to use this regression function as opposed to others you could use in the R language. And so as you can see up here, you will get some confirmation about what the regression model was that you estimated. Then you come down to the background section. It indicates what is the name of the data frame. We knew this was called df. We named that ourselves. Then you'll get your response variable, which is another way of saying outcome variable, its performance. And then it lists the different predictor variables. In this case, we have 3 predictor variables, SJT, EI, interview, as well as the number of cases or rows of data in our data frame and how many were retained for the analysis, both of which were 300. This just indicates that we don't have any missing data on any one of these variables that we specified in our model. Now, what's going to be the first area of substantive interest here is the basic analysis section here, and specifically the subsection called estimated model for performance. So this is where we're going to get our parameter estimates, or our parameter estimates, or you can call them regression coefficients, regression weights, as well as our intercept value for our model. And so this is a y-intercept value here. You can see the estimate is 5.602. You get your associated standard error and t-value, significance test here with associated p-value. And so we typically aren't super interested in whether or not the intercept is significantly different from 0, at least in the context of the type of, with the goal that we are focusing on today, which is whether there's incremental validity with respect to the predictor variables in relation to the outcome. What we are really interested in is if we go predictor by predictor variable, so here's the situational judgment test or SJT predictor variable, its regression coefficient estimate here, which is 0.485. If we go all the way over to its associated p-value, see the p-value is less than the conventional two-tailed alpha cutoff of 0.05. And because it's less than 0.05, we would conclude that this regression coefficient here, which represents the linear association between SJT and our outcome of performance, is statistically significantly different from 0, which means that there's a statistically significant association between SJT and performance, and this is the important part, when controlling for the other variables in the model, the other predictor variables in the model, their effects on the outcome. So in other words, when controlling for emotional intelligence variable and the interview variable here. Okay, so now we're down to the emotional intelligence variable here. Its associated regression coefficient is 0.091. Let's come over to the p-value associated with it on the same line. We see here the p-value is 0.70. Well, that is definitely greater than 0.05, which is our conventional cutoff for statistical significance. And because it's greater than that cutoff for statistical significance, this means that we should not treat this as a meaningful association. In other words, this is not a statistically significant association between emotional intelligence and performance when controlling for the other 2 variables in the model, which are SJT and interview. Okay, so right there, this would suggest that there is not evidence of incremental validity with respect to the outcome of performance with the EI or emotional intelligence variable here, because its effect is not statistically significant when controlling for the other variables in the model. So in other words, it seems to be controlling maybe redundant aspects, or it seems to be explaining perhaps redundant aspects of our outcome variable performance that are already explained mostly by the SJT and interview variables. But what that did mean is that there is evidence of incremental validity so far for the SJT variable because it has a significant effect when controlling for the other variables in the model. Now, coming down to our third and final predictor variable in the model, this is our selection tool called interview. The associated regression coefficient is 0.378, and its associated p-value is 0.000, so that is definitely less than 0.05, which is our conventional cutoff for statistical significance. So we can then conclude that the association between the interview variable and performance variable is statistically significant. And this would also indicate that there's evidence of incremental validity for this interview variable with respect to the outcome of performance here when controlling for EI and SJT. Okay, so in other words, this variable interview explains unique variance in the performance outcome controlling for the other predictor variables. Okay, so, but as I noted here, we did not find that for the EI or emotional intelligence variable. All right, so going down here, you can see here is the unadjusted, or what is simply called R squared here, but note this is the unadjusted. You can tell it's the unadjusted because it's not the adjusted R squared. Here's the R squared value, it's 0.265. We'll actually return to this in the follow-up model we're gonna run, and I'll explain it in a little bit more detail. But this is the proportion of variance explained in the performance outcome variable by all three of these predictor variables, SJT, EI, and interview collectively. Okay, so we can scroll through. Not that this output isn't important, but we're going to scroll through it for the sake of time and come down here to the section called correlation matrix. And what you'll find here is the correlations between all of the variables in the model. Okay, so here you can see in the first column we have the correlation. This is the Pearson product moment correlation between the SJT variable and performance is 0.42. By conventional standards, that would be considered a medium to medium large association. The next association is very close. The correlation is 0.43 between EI and performance. So it's also a medium or medium large. And then with interview, it's a little bit smaller. Its correlation with performance is 0.39. That would be considered medium, medium large or so as well. But what we're really interested here in this correlation matrix in this context is, well, let's take a look and see what the correlations are between the predictor variables in the model with themselves. So the intercorrelations between the predictor variables only. Okay, so let's start with the association between SJT and the EI predictor variables here. Wow, we can see the correlation is 0.93. This is a very high correlation. Remember, the correlation, the largest correlation is the absolute value of 1.0. Okay, and this is almost 1.0. And so this indicates a very, very high association between these two predictor variables, especially when you consider that both of these variables were probably assessed using these tools with some degree of unreliability. So look what the association, though, is between the SJT variable and the interview variable here. It's 0.24. That's much more acceptable. That's low to moderate levels of association or correlation between those variables. And what's the association between the EI variable and the interview predictor variable? Well, it's also fairly low or moderate. It's 0.32. But this 0.93 is concerning here. This is so high that we would typically say that the association between SJT and EI with a correlation of 0.93, they're almost statistically indistinguishable from one another. And typically the rule of thumb that I would suggest using is that when a correlation is at or above 0.85, it can typically indicate that the two variables involved in estimating that correlation are virtually indistinguishable or redundant with one another. And so this maybe or likely explains why above here in our estimated model that we didn't see an effect incremental validity explained by the EI variable in performance. It's because it's almost the same variable as SJT. The SJT variable just kind of won, so to speak, in terms of explaining the variance in performance here. Okay, so that's problematic. And when we have a correlation that's that large, it's going to indicate that we have probably concerning levels of collinearity, which is one of those statistical assumptions that we want to avoid collinearity in our models as much as possible. Fortunately, in our output, if we come down to the next section down here, it's called collinearity, and we see two conventional indicators of collinearity, which are tolerance and your valence inflation factor here, or in other words, VIF. Now, we're just going to focus on tolerance here because VIF is simply the reciprocal of tolerance, so 1 divided by tolerance, or you could think of tolerance being the reciprocal of VIF, 1 divided by VIF. And so we'll just focus on tolerance here because I think it's a little bit easier to interpret in some ways. So when we're talking about tolerance, a value of 1.0 for tolerance in terms of collinearity is actually a good thing. It means that there is essentially no collinearity. We get concerned with tolerance and get therefore concerned with collinearity when our tolerance value falls below 0.20 and closer to 0. Because if it goes below 0.20, this is typically an indicator of strong collinearity involving this variable in the model. And so here what we can see is that the tolerance for SJT is 0.127 and the tolerance for EI is 0.121, and these are definitely both below that conventional cutoff of 0.20 for tolerance where we find things concerning. And so this suggests that there's probably an issue between these two variables because the third variable here has a tolerance of 0.873, which is pretty acceptable and normal. It's approaching 1.0, which would indicate low levels of collinearity. But again, what we're seeing here is just a different way of essentially looking at that correlation of 0.93 we saw between SJT and EI above. And this is indicating to us that these two variables are essentially indistinguishable from one another. And so what we're going to do now is, in this context, we want to re-estimate the model where we don't have such an issue with collinearity here. And because we're focusing on employee selection tools here and we're trying to come up with the most effective predictors of future job performance as should we administer this to future applicants, and we're trying to make sure that we can do so not only effectively but efficiently as well. Well, it's not very efficient to pay to use two different selection tools, a situational judgment test and an emotional intelligence test. It's not efficient for the applicants either in the future who would have to take their time completing both of them. And since they both, we know conceptually, measure emotional intelligence, it stands to reason that we should probably just drop one of them. Let's say that in real life that the emotional intelligence test, for whatever reason, it's something we bought through a vendor and it costs quite a bit of money compared to the situational judgment test that we developed in-house in terms of cost per applicant. And so therefore we make the decision just to go, for financial reasons, with the SJT variable or selection tool instead of the EI. Okay, and this is just for the sake of explanation here. This doesn't necessarily generalize to real life in terms of the true cost of these two types of tests. So let's estimate a second model in which we simplify it by dropping the EI predictor variable, the emotional intelligence predictor variable, leaving just the predictor variables of SJT and interview. So I'm going to copy, to make things easier, lines 60 and 61 here, which contain the multiple linear regression model. And I'm going to make a note here, dropping EI variable, okay? So we're just gonna drop the EI variable by deleting it and one of the plus signs there. And so the next thing that we're going to do is let's go ahead and rerun this model here. And I'm just gonna clear out the console here. You don't need to do that necessarily, but I'll do it just so I can find things more quickly. Click run. You'll see that you get the same plots as before. We'll continue to ignore those for just the sake of this tutorial here. And let's start from the top here. We get our model confirmation. We get confirmation about the variables in the model. Now you see we just have two predictor variables, SJT and interview, still retaining the same number of cases or observations for analysis, which is 300. Now let's get down to the basic analysis section and start with the estimated model for performance here. So this is where regression coefficients are and a regression model is in terms of its estimates. We get our intercept value is still going to be on the first line here. But where we're interested now is, and this, we don't expect, both of these two predictor variables showed evidence of incremental validity with respect to performance in the original model with 3 variables, so it's not too surprising here that we'll find that SJT, the regression coefficient, this is an unstandardized regression coefficient like the last model, it is 0.567, and the associated p-value is 0.0. So again, this is less than the conventional p-value cutoff of 0.05, so still SJT shows incremental validity, and this time it shows incremental validity with respect to performance over and above the variance that's explained by interview as the other predictor variable. And then interview, conversely, its associated regression coefficient is 0.385. Its associated p-value is less than 0.05, so it is also statistically significantly different from 0. And so also the association between the interview variable and job performance here does show evidence of incremental validity over and beyond the SJT variable here. Well, let's practice kind of talking through now these associations in a little bit more detail. And so what do we mean by these significant associations? So let's start with the association we found, the significant between SJT and performance. Well, this is a positive association here. This regression coefficient value is positive. In other words, it's not negative. There's no minus sign in front of it. And as I mentioned, the p-value is less than 0.05, so it is statistically significant when controlling for the other predictor variable in the model, which is interview in this case. And conventionally, we'd write out the notation something like this, using a b, lowercase or uppercase, because these are unstandardized coefficients. B is equal to the regression coefficient. P-value is equal to or less than, in this case, because the p-values are 0.000. They're not exactly equal to 0. It just means they're very small, and due to rounding, we only see 3 zeros here. And so conventionally, we'd just write this as p is less than 0.001. And then we also get the 95% confidence interval over here, which ranges from a lower limit of 0.401 to an upper limit of 0.734. Okay, which means the true population value or parameter likely falls somewhere in that range there. And this right here is our point estimate that falls right in the middle of that 95% confidence interval range. Okay, so let's now interpret this slightly different here. The same association we're focusing on between SJT and performance in a slightly different way, but sometimes a way that's helpful for communicating the linear nature of these associations. And that is, we could also say, or in addition to this, the explanation we gave above, such as if we're giving this as an oral presentation or a written report, we might say something like, when controlling for the effects of the interview scores, for every 1 unit increase in the predictor variable of SJT, the outcome variable of performance increases by 0.567 unstandardized units, or just simply 0.567 units. And so you can see right here, the 0.567 is our regression coefficient value for SJT. And it's important, though, to make it clear that you are controlling for the other predictor variable, or in the case where you have 3 or more predictor variables, for the other predictor variables, plural, in the model when you're interpreting this, because this helps get at that idea that you are finding evidence of incremental validity. So I'll just note here, this is evidence of incremental validity here. Okay, so now let's do the same thing and let's sum up what we found for the second significant predictor in the model, which is interview. It was also positive. The regression coefficient is positive here. It's 0.385. Associated p-value is also less than 0.05. So we found that when statistically controlling for the other predictor in the model, which is SJT, the interview variable was positively associated with the outcome variable of performance. And here you see the common notation we typically include in terms of the technical write-up: regression coefficient, again, the associated p-value, it's less than 0.001 in this case, and the associated 95% confidence interval is 0.260 to 0.511, which you see written here in this bracket notation. Here's the lower limit, 0.26, upper limit, 0.51. Okay. All right, so another way that we could say this, just to continue practicing this language, and I suggest explaining it in both ways typically to get used to it and to help your audience understand. We could say controlling for the effects of the SJT variables, predictor variable scores, for every 1 unit increase in the predictor variable of interview, the outcome variable of performance increases by 0.385 units. And again, these are the units. The unit is the regression coefficient here. So you can get an idea of kind of that linear association. For one unit increase in the predictor, the outcome increases by 0.385. If this was a negative association, it would be an inverse. So for every 1 unit increase in the predictor variable, a negative 0.385, for example, decrease in the outcome variable. Okay, so now let's move down to model fit here. I mentioned earlier with the first iteration of this model that I would explain model fit in R squared in a little bit more detail. And so here you can see the model fit section. We're really interested in the unadjusted R squared here, which again is just to the left of the adjusted R squared. And so the unadjusted R squared value is 0.264 here. And so what is the unadjusted R squared value? Well, the unadjusted R squared is an indicator of the model's fit to the data, and it also indicates the extent to which the predictor variables, because this is a multiple linear regression model, the extent to which those predictor variables explain variance in the outcome variable. It can also, because this is a standardized metric, it can be used as an indicator of practical significance or effect size at the model level. So what I mean by that is collectively, what is the effect of all the predictor variables in the model in relation to the focal outcome variable in a multiple linear regression model? Okay, so we can see, as I mentioned, the R squared is 0.264. So what does that mean? If this is an effect size, what are some conventional thresholds or rules of thumb that we can refer to help interpret this? Well, we can think of the R squared values as being a small one would be 0.01, a medium, once you get to about 0.09 and larger, you could say it's a medium-sized effect, and when you get to 0.25 or larger, you would say that's a large effect. So in this case, we found that the R squared value was 0.264, so I'll make a note here. So that 0.264 is definitely greater than 0.25, so we would call this a large effect. And so what's another way we can explain this? Well, R squared, you can think of it, as I mentioned below or above, as the percentage of variance explained. And so we could say collectively, the SJT and interview scores explain 26.4% of the variance in performance scores. So performance, again, being your outcome variable. And so all I did here was convert the proportion of 0.264 to a percentage of 26.4% by just multiplying it by 100. And sometimes this is a useful way of explaining to other people who maybe are not as familiar with regression or these types of models, just how effective these, in this case, selection tools are of SJT and interview selection tools of predicting performance, or in other words, explaining, in this case, variance in an outcome called performance here. Okay, so this is actually pretty good here. We get pretty excited about this. This means that we can be a little bit more confident that if we use these two tools of situational judgment test and interview test here, and we give this to future applicants, that hopefully we'll be able to improve the likelihood that we can make good predictions regarding which of the applicants is going to be a better future performer should they be hired. Okay, so that is essentially, this wraps up this portion of this tutorial in terms of trying to understand a multiple linear regression model, as well as understand how a multiple linear regression model can be used to evaluate whether there's evidence of incremental validity with respect to the relation between each predictor variable and the focal outcome variable when accounting for the other predictor variables in the model. But now I'd like to do kind of an optional detour here, which is to show you how to get standardized regression coefficients. So I'm going to now note that we will estimate a multiple linear regression model, and I'll just note that standardized coefficients is what we're going to request. So by default, and this is the case with most regression functions and linear model functions that I'm familiar with, at least in the R language, that they will by default give you your unstandardized or raw regression coefficients, meaning they haven't changed the scale or the scaling of any of the variables in the model. They haven't standardized them, turned them into z-scores, or centered them in any way, whether that's grand mean centering, or if you're talking about multi-level models, perhaps group mean centering as well. So what we're going to do now is just grab the last model we were running. This is just for the sake of explanation. Doesn't really matter which of the two models. Paste it here. And to get standardized regression coefficients, I'll just add a third argument by adding a comma here. And I'll just go down a line, so hopefully this is a little bit easier to see. And it's just called rescale, because that's what we're doing here. We're going to rescale equals, and then add quotation marks and z, because we're just going to rescale the outcome variables and the predictor variable, the outcome variable and the predictor variables into z-scores, so standardizing them. And this will allow us to interpret them in standard units or standardized units. And so another way you could get around this is if you wanted to prep the data ahead of time, you could just standardize these by using, for example, the scale function or a similar function in R and rescaling these variables yourself. But fortunately, the regression function here in lessR has a built-in rescaling argument here. Okay, so watch what happens if we click run here. You'll see you get similar output. And the first thing you'll notice that's different is it gives you an idea of the first 6 rows of the data frame, what the rescaled scores look like. And then you'll see the background variables. This is going to look identical to what you saw with your traditional default unstandardized regression coefficients model. You'll get a little note here that the data are standardized now as confirmation. Where you're going to see some changes is in the estimated model performance here. You'll see the intercept value is equal to 0 here with a p-value exactly equal to 1 because it's definitely not significantly different from 0 because it is 0 here. So when we standardize the coefficients, our intercept becomes 0. And here you'll see that the coefficients are now standardized. And so you can see that the p-values are still the same as we saw with our unstandardized model. It would just be the interpretation that changes a little bit. So instead of saying for every 1 unit increase in SJT, performance increases by whatever it was in the previous model, 0.56 something, in this model we'd say for every 1 unit increase in SJT, performance increases by 0.344 standardized units or standard units. Okay, so we just changed the language there slightly by adding standardized language. The same goes for the interview variable, but you could still interpret whether or not there's evidence of incremental validity here because, again, the associated p-values stay the same because all we did was just change the scaling of the variables. You'll see the R-squared value, the unadjusted R-squared value is exactly the same at 0.264. We're going to see the collinearity, tolerance, and so forth are going to be exactly the same. As you can see in these models, I forgot to show this in the previous model that was unstandardized. Tolerance is now almost 1.00 for both of the predictor variables in the model after we kicked EI out of the model as a predictor variable. So this means that we have very low levels of collinearity here. And you see this reflected in the association between SJT and interview in this correlation matrix in the output. The association is 0.24, which is very acceptable level. All right. So we can ignore in all the output. The rest of the output that you would have found in any one of these models includes more information about diagnostics for statistical assumption testing, such as looking at the residuals and so forth. And so you see Cook's estimates there, for example. And then down here we have a forecasting error table and output where you can get some prediction intervals and so forth as well if you're interested in that. All right, well, this wraps up this tutorial on how to evaluate whether there's evidence of incremental validity using multiple linear regression models. And in this case, we focused on the applied context of employee selection tools in the sense of assessing their incremental validity. In other words, is it worthwhile using all of these tools? And what we found here today was that we started with 3 selection tools: the SJT, situational judgment test tool, the emotional intelligence test tool, and the interview test tool. And we came to the conclusion that really the EI tool was redundant with the SJT tool. And we came to some conclusion that behind the scenes, it was cheaper to use the SJT tool. And given that it was so strongly correlated with the EI tool, we dropped the EI tool. And now we're down to 2 selection tools. All right, well, this wraps up the tutorial.